I want to use toluene to illustrate a couple of features because there are some annoying things that happen in real spectra that complicate your interpretation of things. So first, how many unique environments are there? Well, there's clearly the methyl, and in terms of chemical shift, that's going to be around 2 to 2.5, whereas the rest of this should be right around 7 because it's on the ring. So there are going to be 3 hydrogens in this environment. So this is environment 1, and there are 3 hydrogens in it. Meanwhile, this whole molecule has a plane of symmetry running smack down the middle of it, and therefore these 2 hydrogens are going to be related to each other across the ring. But this hydrogen down here is going to be the 4th environment, and it's going to be all by himself in a 1H sort of mode because he's alone there. Meanwhile, these 2 hydrogens are in the same environment. They're both in environment 2. Therefore, this thing is going to integrate for 2H, and these 2 hydrogens are likewise in the same environment as each other and in a different environment than everyone else, and total, again, that needs to add up to 2H. Therefore, if you're thinking about the molecule as a whole, you're going to have a total of 8H across the entire molecule, but you'd expect it to be arranged in 3, 2, 2, and 1. So why is this complicated, and why am I illustrating anything with this molecule? Well, because all of these hydrogens, all 5 of these, are going to be in a very similar environment to each other, and so though it could show up as 2H, 2H, and 1H in nice distinct peaks that are easily resolved and you can understand, the other thing that could happen is this entire group of peaks could all lump together in one spot in the NMR and basically integrate for 5H. And it doesn't have to work that way either. You could have, say, this one and this one ending up in the same spot, or these 2 ending up in the same spot, or whatever. The only thing that I'm sure of is this molecule is going to have 3H down around 2 and 5H in the 7-ish range, although if everything works out the way you'd expect, you would expect 4 different unique environments, 3H, 2H, 2H, 1H, as what you would expect. Although you should be prepared to accept things landing on top of each other coincidentally because their chemical shifts are relatively similar. And all of these chemical shifts for these hydrogens are going to be pretty darn similar to each other. This, by the way, depends a little bit on the solvent that was chosen to run the NMR in, so that can complicate things as well.
So given what I'm about to talk about, it will be useful to go ahead and add some multiplicity information to these peaks. So if you've watched the multiplicity video, then you can figure this out yourself. But if not, then the key thing to realize here is that each one of these signals is going to have a multiplicity associated with it. The 3H of the methyl group is actually going to be a singlet, whereas each of the groups in the aromatic region is going to be more complicated. You would anticipate that these 2, the hydrogens in location 2, should be a doublet because they have one nearby neighbor, this red one. So this hydrogen has this as a neighbor, this hydrogen has this as a neighbor. But anyhow, we would expect that to make this a doublet. Position 3 experiences both 2 and 4 as neighbors, therefore you'd expect that to be a triplet. Position 4 experiences both position 3 hydrogens as neighbors, and therefore you'd expect him to be a triplet as well. So in other words, the boring methyl down on the right hand side is going to be a singlet, but we would anticipate seeing a doublet worth 2H, a triplet worth 2H, and a triplet worth 1H. However, it's at this point that I'd like to go ahead and give you sort of the main reason why this video exists. Fundamentally, integration is hard. And of all 3 topics, the one that students struggle with most, especially when they start looking at real spectra, is integration. Students usually can grapple with multiplicity and extract some interesting information there. They can rely on tables to figure out chemical shift, but integration is fundamentally hard because you can't just rely on the computer. It is the one where you have to inject the most thought in order to figure out along the way. But integration is also the thing that I and Professor Pelkey and Professor Miller and experts in general rely on the most because it's the one thing that has to work out in the end. It has to. Chemical shift, there's some flexibility. Multiplicity, there's all sorts of reasons why things could look different than what you'd expect. But ultimately, integration has to work out. Therefore, we rely on it a ton. This is the thing that if it's wrong tells you that you're wrong about whatever you're looking at. So we rely on this enormously. But for students, it's really hard to figure this out. And in the first video, the easy integration video, I was largely focusing on impurities. I pointed out a couple of times how a tiny little peak could confuse you if you thought it was a real peak. And usually if you have impurities in your spectrum, they're easy to spot because their integrals don't work. But it can actually be really confusing if you have an integral that just happens to integrate for the right amount of your stuff. So anyhow, peaks that don't belong as part of your stuff can throw off your integration. That can be a problem. However, in many ways, the more dangerous thing, the harder thing to deal with, is the thing I'm about to illustrate with the toluene, and that's the reason why this video exists. If peaks lump together in funny ways, that can definitely throw off your analysis of the compound. And so that's really what I'm trying to do here. We're going to look at the aromatic region and see that these peaks end up lumping on top of each other and not necessarily in the way that you'd expect. So the core thing I'm showing you right here with this spectrum, and again this is toluene, is that you have the peak around 2 that integrates for 3H, that's the methyl that's not on the ring, and then in the region around 7.2 or thereabouts, there's a general lump that integrates for 5 altogether. And this is going to be true in all of the various solvents that I used. This particular NMR is CDCl3, but I chose 2 other solvents as well, and I really want to zoom in on the aromatic region, the region around 7, so we can focus our attention there. And this to me looks like a horrible, indistinguishable sort of lump. But I could, if I wanted to, break this up into 2 smaller chunks. So let me integrate that. Although before I do that, I want to point out that this earlier chunk seems to integrate for 2, and the later chunk seems to integrate for 3. If I'm looking at this curve, this part of the curve is taller than this part of the curve. So when I go ahead and break this up, I'm going to call the earlier part 2 and the latter part 3. So I click and drag across to the low point here, and that should be about 2, and I click and drag to there, and that's going to end up around 3. Even though at first it looks like a horrible undifferentiated lump worth 5, I could actually resolve it into 2 terrible looking lumps, one that integrates for 2 and one that integrates for 3. What that means is that somewhere in the actual spectrum we've got overlapping peaks, and or things are making this complicated for other reasons. So let's change solvents a little bit. And what I want to point out here is that, again, if you're calling this front part 2, then the total of this back part is 3, but you can now start to see this peak right here lurking, kind of hiding underneath. This is actually a triplet hanging out underneath this thing right here. So I would call this a triplet if you've looked at the multiplicity video. It's definitely not a normal triplet. It's distorted. There's some weird stuff going on, but it definitely has a triplet sort of appearance to me. And likewise, under here is a triplet that's hanging out and being obscured by the fact that there's a doublet sitting on top of it. So this integrates for more than it should, like 2.4 or so, and this integrates for less than it should, 0.7, and that's because a substantial part of this peak is hanging out right here and is hidden. This is kind of what overlap looks like. Here, the overlap was complete. There was no hint that there were 2 peaks lurking. Here, this is starting to resolve itself. And the main reason why I'm showing you this is because in DMSO, they're starting to get further apart, and in acetonitrile, they are almost completely resolved. Again, the triplet out here that integrates for 2, he's fine. And then we have a doublet that is largely left of the triplet that you can see lurking right there. Is this well resolved? Does it go down to the baseline? No, it does not. But this is clearly now a triplet worth 2, a doublet worth 2, and a triplet worth 1. So acetonitrile comes the closest of the 3 spectra to having the aromatic region resolved into 3 separate peaks, a 2H triplet, a 2H doublet, and a 1H triplet. And the one that comes the worst is the one in CDCl3, where the triplet and doublet part of these peaks are unresolved and just kind of mashed on top of each other, and you really can't resolve things. And by the way, it could be worse. There could be a spectrum of toluene in which all of the 5 peaks end up lumped together. So everything is possible. So the last thing I want to point out about the integration is if you're actually doing the integration, look how many choices there are along the way. I had to decide whether to treat this as one undifferentiated lump or whether to cut it in the middle, decide where exactly to cut it. I didn't even show you that for all of these, what I'd done was integrate the singlet off screen, that's 3H, and I use that as the reference point with which to do everything else. And that's really what I recommend for you. If you're trying to figure out what it is that you're looking at, the really important thing is to find a peak that you know what it is. So I knew ahead of time that this was a methyl singlet, which then allows me to make all of the decisions over here. So globally, that's the way to treat integration. You find a peak that's your touchstone, a peak that you know unambiguously. It's often a methyl, but it can be a 1H peak or a 2H peak as long as you know what it is and can reliably use it to set a reference. Once you've done that, then you can start carving up peaks that kind of lump together, which allowed me to realize that what I was looking at here was a 2H and a 3H peak. And then with that in mind, I can look at this and start to recognize that these side things are probably a peak that's lurking underneath, and I treat them as separate peaks. But then I can even carve this up further, although then I realize from the integrals that they really aren't two completely differentiated peaks, but instead overlapping. And so that's why integration is so powerful. The fact that this whole thing integrates for 3 tells me that there are 3 hydrogens there. The fact that this part of this thing integrates for 0.7 means I have not yet found all that belongs in this peak. The smallest number that you can have is a 1H. So if I've got a 0.7, that means I'm wrong about something. And then again, here what I'm able to do is actually differentiate all 3 peaks from each other. And now it's pretty clear that the cut line should be right there, because that leads to a triplet worth 1 and a doublet worth 2, both of which are plausible. Back here, when I tried to do the same sort of cuts, I got a doublet worth 2.4, which is unlikely, and a doublety thing worth 0.7, which is just not happening. So together, that led me think, actually what I have here is a triplet lurking that's worth 1 and a doublet worth 2. So this is the power of integration. And if what I was just doing there doesn't make a whole lot of sense, well, a little bit more practice from now, and I bet it will start to make sense, in which case, then you're on top of integration. Again, it's hard to learn in the first place, but once you have it, the pros rely on it.